Yeah.
Yes, it's being recorded. Okay, so welcome to yet another wonderful and great One World seminar. Today our speaker is Eran Shmaya. Eran completed his PhD under the supervision of Ehud Leor. He has subsequently went on to be at Northwestern University and Yale University, and now is at Stony Brook University, and has written many papers on manipulations and on learning and merging and all sorts of groovy subjects like that. Today he's presenting his papers. So go ahead.
Okay, thanks for coming. Thanks for the invitation. This is a joint paper with Yini from Northwestern. And maybe before I start, I'll just explain what partial truth in the title mean. Well, partial truth means that there is an agent in my model who can only tell the truth, but he doesn't have to tell all the truth. Okay, so nothing but the truth, but not necessarily all the truth. And if you want to remember one thing from this talk early in the morning is that we are working on this area. So what do we do with it? We have two protagonists in our story, whom you all know. They are called agent and principal. And what these guys are up to is choosing an action out of some pool of action, some pool of available actions. And what drives the interaction between them is that principal is the guy who have the power to make the choice which action they will implement, but agent is the one who knows which are the available actions. So an example just to keep in mind is a department chair and the dean. The dean, and they want to hire somebody out of a pool of candidates. The dean is the one that is going to make the decision whom to hire or whether to hire nobody. But the department chair is the one who knows which are the pool of candidates. And they may get different utilities from different candidates. The department chair will offer some candidates to the dean, and the dean is going to choose one of them. And when I said partial truth, I mean that the department chair cannot invent candidates that don't exist. He submits packets of existing candidates, and he gives all the information about these candidates that he gives to the dean. Okay, so this was very vague, so let me plunge into the model. Let's see if it works. Okay. Let A be a universal set of verifiable candidates. And I will explain later what I mean by verifiable. But this is all the potential CVs that candidates can have. And I will start my description of the story with my agent. The agent has a utility function. The agent has a utility function from each candidate. Is going to be an expected utility maximizer. So this is a von Neumann-Morgenstern utility. And I normalize the utility from not taking any action to 0. And here is the description of the interactions. First, the agent have a set of available candidates, available actions. And this set of available actions is the agent's type, private type. The agent is going to propose a subset of this set of available candidates, available actions. Sorry, I'm going to switch from candidates to actions. So the agent is going to propose a subset of actions. And when I say earlier that actions are verifiable, what I meant is that he can only propose actions that are available for him. Okay, he can only propose a subset of A. And then the principal chooses an action from distribution that may depend on the set of candidates that the agent proposed. And I'm going to write here star for distribution, because when I say distribution, I actually mean sub-distribution. I mean that the sum of all the probabilities should be at most 1, and all the rest is the probability that he will not choose any action, and if he doesn't choose any action, the agent gets payoff 0. Okay, so every time I say distribution in this talk, what I actually mean is sub-distribution, but I will forget about it, so I leave it to you to remember it. And the one thing I forgot to tell you is that the agent, the principal at the very beginning, commit to this choice rule row. He commit to what he will do given any set of actions that the agent will offer him. Okay.
Wait.
There's a question?
Is A known to both agents?
So I have here 2 A's.
The capital A, the universal space of
the
action.
universal set, yes, it is known to both
It's
the
known
agent
to
and
both,
the principal.
and
Yes, but the set of available actions is only known to the agent. And the agent can only propose actions that are available. Okay, so maybe I will.
Okay.
So this would have looked nicer if it was. Yes, Shmuel.
So the probability distribution, which depends on P, may be also defined for P, which is not subset of A or something.
Yes,
right?
the probability distribution at the beginning, well, it is defined for all
because
P
A is not known to the principal.
Yes, so it's defined for every
subset of script A, right?
Of the universal, yes, of the universal set of actions.
Okay, that's what I want. Okay, thank you.
Okay, so you already see where this issue of partial truth comes into play. The agent can only offer actions that actually exist, but he may hide some of them. He doesn't have to offer all of them. We will add possibly other restrictions on the set of candidates, or the set of actions that the agent can propose. And we'll talk about 2 environments. One environment which we called one action. One action environment. When I say that I'm working in the one action environment or one project environment, I mean that P must be a singleton. So the agent can just come and offer a single action, and then the principal just have to decide whether to take it or not. And when I say many actions, I mean that P can be any subset of A. Okay, I will work in these 2 different environments. And the one action environment is I view it as an exogenous restriction. There is some rules in the university that the chair can only come with one candidate.
Eran, I have a question. Where does your commitment come in your story?
So this is here.
I see the assumption in your math, but in your example, the dean and the hiring, where does the commitment come there?
So the example is not supposed to be an application of this model. It's just to fix idea. Maybe the dean doesn't have commitment power. I don't claim that the example is a good application. I just give it to fix ideas. In the paper, we will have more profound words like mergers and acquisitions, and that would be the application. If you don't find the example useful, then don't think about it.
I just wanted to have the motivation of the commitment.
No, there is no motivation. This is abstract, completely abstract.
Eran, can you precise what is the utility of the principle?
I didn't say it yet. I will get to it.
Okay, and what does he know about the set capital A? He has a belief, or...
So I didn't say that either yet.
Okay.
But I will get to it. I didn't close the model yet. So in this environment, under this mechanism rho, some choice function would be implemented. So I will denote the choice function is a function, I denote it by f. This is the function that given the set of available actions, what would actually happen? So this is for every set A of available actions, the agent, given this mechanism, he will propose a set P. Now, which set P he will propose? He will propose the set P that gives him the maximal payoff, right? So he'll propose the set P that is going to maximize the expected payoff to himself. And this is the expected payoff to himself, right? It's the sum over the probabilities that we'll pick action A times the utility to the agent from action A. And this argmax goes over all the set of actions that he can propose. So these are subsets of A. And if he's in the one action environment, then these are only singletons. Okay.
And
so
the sum is A in P?
The sum is A in P, yes.
Okay.
Okay. So given the mechanism, something will happen. For every set of available action, there would be a distribution over actions in A, right? So for every set of available actions, we will end up with some distribution over let me write it. For every set of actions, I will end up with a distribution over A. This is the choice function that the mechanism rho implements. Okay. And the first thing that I will ask myself is just to tell you a bit about which choice functions can be implemented. That's why in answer to Jerome's question, I think it was Jerome, I don't yet have to tell you about the goal of the principles because I'm just looking at this object choice functions and I'm asking myself which one of them can be implemented. Okay.
Implemented by the principle?
By the principle under some mechanism yet, yes.
But what do you mean by implementing a choice distribution? Because basically the principle by fixing the distribution kind of makes the agent choose some subset P.
Well,
right?
The principle commit to this thing, which action he will choose out of the set of available actions, out of the set of proposed actions, P. Now, given the set A of available actions, the agent is going to choose the set of actions that he proposed in order to maximize the agent utility. And now I'm asking myself which functions from available actions to distributions over available actions can be implemented under this mechanism. You see what's going on here? I'm starting with a set of available actions. The agent is going to choose the set of proposed actions in order to maximize the agent's pair. And now the mechanism will pick an action from this set according to the distribution of the mechanism, okay? So these are two different things. The mechanism, which is which action will be chosen given the set of proposed actions, and the choice function, which is which action will end up being implemented given the set of available actions.
Why is that then a function from A? It's from the subsets of A.
Yeah, so I wrote this notation. It's from subsets of A. For every subset of capital A, of calligraphic A, for every possible set of available actions, it gives a distribution over available actions, okay? So for every set A of available actions, f of A is distribution over A.
And you assume the principal knows the utility of the agent.
Yes.
Do you also assume that the principal can force the agent which P to choose in this argmax?
No.
Yes.
Why?
I mean, what do you mean can force the agent? He forces the agent to choose the environment forces the agent to only choose a set of proposed actions from the set of available actions.
Yeah, but the question
is what's good for the agent.
Yeah, but the question is which of the subsets in the argmax the agent will choose.
If there is different if there is possible argmax, then each one of them is legitimate.
Sorry, I didn't get the question. Why has the principal to know the utility of the agent? I don't see it here.
Yeah, no, it's not.
Know.
It's not.
He has this row, and that's it. Well, why?
You are right, Shmuel. For now, I don't need. You are right, Shmuel. For now, it doesn't matter whether the principals know the utility of the agent. Later, when I say the principal chooses row, yes,
sure,
you're right.
Sure. Then this should come later. Yeah. Okay.
You're correct. For now, it doesn't matter. And if I understood Ilan's question earlier, if there are several argmax, then all of them are possible, and you can implement several choice functions.
So the principal can enforce a choice of which one to choose.
Let's not argue about the.
No, I'm asking about the notion of implementation.
Okay. Yes. I think the answer to your question.
Assume the agent is indifferent between all actions. Is everything implementable?
Yes.
Okay. Thanks.
Can you please explain again why F, the domain of F is A, and not the power set of A?
So you see this line that I make as a bold line. What I mean by that is that F maps a set A to a distributions over the set A. I don't mind writing it also as F is a function from the power set of calligraphic A of all the possible actions to distributions.
I understand. Thank you.
Okay. So this is a choice function. I want to make a few comments about the model. So let me go back to my screen with the description of the mechanism. You see that the set of proposed actions here has two roles, or it has two. It plays two roles in my story. One role is that the set of proposed actions gives some evidence to the agent's type. Different agents can propose different things. And this relates to the literature about mechanism design with evidence. Unlike the standard mechanism design, where every agent can claim to be every other agent, here, not every agent can say the same thing. Okay, so P is already contained some way for the agent to give a hard evidence about his type. And I will get to this issue in a moment. But before that, I want to say that P has another role in our model that doesn't exist in other mechanism design with evidence paper. And that is that P also restricts the set of the actions that the principal can take. Okay, so P has two roles here. One is related to the fact that there is an asymmetric information, and it's a way for the agent to give hard evidence about his type. And another doesn't even relate to the fact that there is asymmetric information, but it adds some bargaining power to the agent. The agent can force the principal to take an action out of some set.
You didn't say that. So the principal, the dean cannot hire somebody who is out, not on the list of the chairman.
Yeah, the dean cannot hire somebody who is not on the list, or
he can decide not to hire. I mean,
he can decide not to hire. Yeah, I guess. Yeah, so he has some default action, which is.
So that's what you said. The probabilities does not add to one. Okay.
Yes.
Okay. Okay. Thank you.
So let me talk a bit about this messaging structure. First, in the many actions case. In the many actions case, forget for a minute the fact that the agent also restricts the actions of the principal. Just think about the set P as a message that the agent send to the principal. So when the agent send the message P, the principal gets evidence that the type of the agent, A, contains P. Every message is some hard evidence. Once you see P, you know that the type of the agent contains P. One interesting feature of this messaging structure is that the agent, if he wants, he can send all the evidence that he has. He can send the maximal evidence that he has by just reporting his own type, by just giving the set of all available actions to the principal. This is the maximal evidence that the agent can give. And this property of the messaging structure, that the agent is able to give the maximal evidence that he has, is sometimes called normality. Notice that this normality doesn't hold in the one action case. In the one action case, the agent can prove, look, I have this action, and he can prove, look, I have a different action, but he doesn't have a way to prove that he has both action available. Okay, so in the many actions case, we have this property that is called normality. This is not our terminology. This is the terminology from the evidence literature. And another way to look at normality, or maybe not that different, is to say that since in the many actions case, an agent can propose any set of actions, we can think about it when the agent proposes a set P as if the agent is saying, P is my type. I am of type P. P is the set of available actions. And what's different here than in standard mechanism design is that in standard mechanism design, every type can claim to be every type. Here, not every type can claim to be every type. Each type can only claim to be types that are smaller, right? It can only claim that the set of available action is smaller than it is. which means that the relationship one type can pretend to be another is a transitive relationship. And transitivity is called also nested range condition in some of these papers. So I'll just write here nested range condition. And I will get to these things in a moment. And the one action environment doesn't satisfy these conditions. So one thing that we will do in the paper is we will see how these conditions from the evidence literature affects the optimal mechanism here.
Eran, just to be sure, all of this has to hold off the play path also, right? The restriction that he can only propose available actions, even off the play path.
Yes.
Okay.
Yes, I don't even call this a play path because I view it as
right. Yeah,
kind of
just
exogenous restriction.
Yes. Thank you.
Yes. One more comment. You may think that I could talk about a more general mechanism in which, in addition to the hard evidence, P, the agents also send some chip talk message. You can also you can say the set P, but you can also say, look, I think that you should choose this one out of the set P. Or we can set some under message. The reason you may think that this is the case is because this is the case in standard mechanism design papers, and also in mechanism design with evidence papers, but it's not the case in our environment. And the reason in our environment chip talk would not help, would not enrich the set of implementable choice functions, is that the set P already restrict the set of actions that the principal can take. So once the agent gives the principal this set P of actions, there is no more asymmetric information. The principal now knows all the utility of the agent from all the actions that the principal can take. So in our model, the evidence kills the asymmetric information. After you give an evidence to the principal, now the principal knows the agent payoff from each action. Okay, and this is true both in the one action, in the many actions environment. That's why chip talk in our model would not help, unlike other mechanism design with evidence papers. The additional comment I wanted to make is about the revelation principle. In this many action environments, when you have normality, or equivalently, you have this nested range condition, it is known that the revelation principle holds, which means that we can restrict ourselves to mechanisms in which the argmax here is to choose A. But this is only when the revelation principle holds, so this is only in the many action environment. Okay? In these environments, we will restrict ourselves to mechanism in which it's just optimal for the agent to report the truth. Okay? So now, finally, I'm in the point of my story in which I'm going to talk about the principal problem. So I'm going to add a utility function to the principal. And the utility function to the principal from the set of all possible available actions. Let's see first what the principal would do if there was no asymmetric information. If the principal knew the set A of available actions, then even though in my description of the story, the agent can restrict the principal to pick action from a subset of the set of available actions, this is just a formality. In fact, when there is no asymmetric information, all the bargaining power is at the principal hand, because the principal, if he knows the set A of candidates, is going to tell the agent, look, this is the candidate I want. If you offer me this candidate among the set of proposed candidates, I'm going to take it. I'm going to take it. If you don't offer me this action, I'm not going to take any action, and you go home with payoff 0. Okay, so if we knew, if the principal knew the set A of available action, the principal could have gotten, for every set of available action, it could have gotten the maximal possible payoff. As it happens, he doesn't know. And therefore, under any social function, under any choice function f, is going to suffer some regret. And the regret is the difference between what he would have gotten if he knew the set A of available actions and what he actually gets when he doesn't know. And I should have told you, and I didn't, but I'll tell you now, that we also normalize the principal's payoff to be 0 if no action is taken. Okay, but we assume that both of them gets positive payoff from each action. This is going to be the regret of the principal, and it is obvious that under any choice function, there would be some sets available actions under which there would be regret. It is obvious that he cannot always get the maximal payoff, because if he always gets the maximal payoff, it means that if the agent offers him a single action, then he must take it, because it may be that this is the only available action. But if he takes every single action, then the agent would just pick the action that is good for the agent, which may not be the one that is good for that is best for the principal. Okay, so it's obvious that there would be some regret. Well, what should we usually do in this case? Well, the standard mechanism design literature say, let us take some prior over the set of available actions and try to find the mechanism that minimizes the expected regret, right? Because I don't know what is going to be the set A. I'm going to find the mechanism that minimizes the expected regret, or equivalently, the mechanism that maximizes the expected payoff to the principal. And this is what in a very specific environment, two guys, Armstrong and Vickers, did. And I will tell you later what they did, Armstrong and Vickers. But this is not what we are going to do. We are going to assume that the principal is trying to minimize the worst case regret. And the worst case regret from a choice function f is the maximum over set A of the regret if the set of available actions is A. And the goal of the principal in my model is to pick a function f, which is implemented by some mechanism rho, that minimizes this thing, that minimizes the worst case regret. So to be more explicit, I will go back to my timeline. And I will say that after the principal commit to the mechanism rho, an adversary chooses the set A. And then the agent picks the set P from this argmax. The principal chooses an action, and the principal suffers regret. Sorry. This is my new Apple Pencil, but I still don't use it well. The principal suffers the regret, which is maximum the best thing that he could have gotten minus what he actually got.
Is the agent's utility common knowledge?
Yes, at this point, I mean, not yet, but in a moment when I will say that the principal is trying to find a mechanism that that minimizes the regret, then the principal would know the agent utility. So the principal knows the agent utility means that when the department chairs come to the dean with a description of a candidate with the CV and recommendation letters and everything, then the dean knows exactly how much utility the department chair will get from it. And the dean also knows how much utility he will get from it. Okay, so notice that I started with an interaction between the principal and the agent. Actually, what I have here is an interaction between the principal and an adversary. They play a zero-sum game. In this zero-sum game, the principal starts by announcing a mechanism rho, and then the adversary chooses A, the set of available actions, and then there is an agent, but the agent is very passive here. It doesn't, I mean, what he does is dictated by this rho and A, and we get payoff. The principal suffers payoff. So this is a zero-sum game. I just want to emphasize that I'm not looking at the value of this game in mixed strategies. I'm looking at the max min, right? Or I'm looking at the min max. The principal is trying to minimize the maximum that the maximum payoff, that maximum damage that can happen to him. And the principal moves first, right? The principal announces his pure strategy first. This is rho. And then the adversary moves. Okay, so there is no, they don't play simultaneously. There is no mixed strategies here. The principal announces rho, and then the agent chooses A.
Eran, question?
Yes.
Doesn't the adversary, the view, I mean, how doesn't this enter the zero-sum game? Doesn't it enter the consideration of the chairman of the department, the agent?
No, it doesn't. The agent is not against the principal. The agent just maximizes the agent's payoff. So the agent, in my model, does this. Regardless of what is rho and what is A, the agent is going to do this.
But doesn't that reveal some information about the preferences of the dean that the agent could benefit from?
Sorry?
The way that the dean plays with the adversary should tell me, as if I was the chairman, should tell me something about the dean's information.
The agent knows the dean's utility function from the beginning. The agent knows the dean's utility function. The agent knows the principal's utility function.
Okay, and he knows also all the fantasy possible A's that the adversary can provide.
He knows all this, but I don't think it matters, because in the end, when he comes to the game, there is already the mechanism rho. He already knows what is the mechanism rho, and the principal committed to it already, and he already knows what is the set of available actions. So when he plays, there is no strategic considerations. He already know what is the mechanism, he already know raw, and he already knows what is the set of available actions. He knows that he can choose some P out of this A, and this is the utility that he will get.
Thank you.
Okay, so here is the moment that we all waited for. Let's see if it will work. Sorry. I'm going to try to show you my slide of related literature. Sorry, this is really too early in the morning for me, obviously. Do you see it? Do you see it? Sorry. You see the slide?
We see it. We see it, yes.
Okay, so what do I have here? First, the paper of Armstrong and Vickers. This is the paper that I mentioned earlier. This was our direct inspiration, and it's still probably the most related paper, even though now we are understanding more the relationship to mechanism design with evidence. Another paper of choosing a project out of a set of projects, but not in a mechanism design environment, but with evidence, is this paper by Ben Porat, Deckel, and Lipan. And you see that our paper is in the intersection of two literatures. One is the literature on mechanism design with evidence, and another is the literature on mechanism design with worst case regret. And I wrote here a bunch of papers, and please don't be offended if your paper is not here, because we just wrote it in the last minute. And actually, I feel really bad because my co-author, we arranged it according to year, but I somehow managed to screw this, and I uploaded an earlier version. So sorry about that. This, and maybe some of them are missing. Okay, one more thing I want to say. I would like to have another bullet here that talks about the literature on bargaining, because you see that I did have some, there is some bargaining between the agent and the principal going on here, and both of them has some power. The principal can commit to the mechanism, but the agent also can give, in a way, a take it or leave it offer by giving the set P of candidates, of actions. So so I would like to add here a bullet about bargaining, but we don't have papers yet. We're still looking for it. Okay, so I'm going to take 5 minutes to tell you what Armstrong and Vickers did in a Bayesian environment, and then so I have an hour, right? Or I'm going to assume that I have an hour, but.
Yeah, you have an hour for the talk, but then the discussion is flexible.
Okay, perfect. So I'm going to take 5 minutes to tell you what Armstrong and Vickers did, and then I'm going to tell you our optimal mechanisms. So what Armstrong and Vickers did is they look at a Bayesian environment. So they look at a Bayesian environment. When I say Bayesian environment, I mean they had some prior over the set A of actions. And what is this prior? First, their universal set of actions was the set, was a product set. And each element here, you could think about it as an action. We identify the action with the payoff that it gives to the agent and the principal. So U is the payoff to the agent, and V is the payoff to the principal. Okay, so this is the set of actions. And you see what is the function u and v, right? It's just a projection over the coordinates. So we identify every actions with the payoff it gives to these two guys. Okay. And the payoff is in this rectangle. It doesn't matter what, I mean, this under u is some parameter. And they assume that actions first are IID from this set with some distribution over this set, over this rectangle. So actions are IID, and the number of actions is independent of the realizations of the actions. Okay, so there is some number which is distributed according to some of the standards distributions that we know. I don't know, geometric or Poisson or uniform. This is some integer. And then given this number, we randomize IID actions from this set A. Okay. And they looked in the one project environment, one action environment. So the agent can only offer one action. And they restricted themselves to deterministic mechanisms. And when you restrict yourself to deterministic mechanism is just you give me an action and I just tell you whether I will agree to it or not. Okay, so deterministic mechanisms are essentially just a set of possible things, a set of actions that I will be willing to take. Okay, so this is what's called sometimes the delegation solution, because the principle essentially, when he restricts himself to deterministic mechanism, the principle essentially tells the agent, look, I will only agree to actions from this set D of actions. Now pick whichever action you want from this set D of actions. And their solution, they solved for the optimal delegation solution. And one interesting feature that they got is that it is of the form it is of this form. So for some function R, so you are willing to accept a project if it gives the principal sufficiently high payoff. How much sufficiently high depends on the payoff that it gives to the agent. And they write some control problem that identifies this function R. Okay. And what we are going to do is worst case regret with the same set calligraphic A of available actions. Okay. And let me write you our theorem for the one agent environment. One action environment. So now we are looking at the one action environment, but we are not looking at deterministic mechanisms. We are looking at Bayesian, randomized mechanisms, like I said before. And I'm looking for the mechanism that minimizes the worst case regret. And here is the theorem. I'm looking now at another game. In my original zero-sum game, which had a huge set of strategies for the agent and the principal, for the principal and the adversary, in my original zero-sum game, the principal moved first. He chose a mechanism, and then the adversary moved and chose an action. Now I'm looking at a much smaller game, which I can solve on Mathematica. This is a game in which the adversary just chooses one number V, and the principal chooses between these two. The principal now has only two actions, either this or this. Okay, and I'm looking at the value of the game, and if you do the calculation quickly, it turns out to be this number. But it doesn't matter. I mean, the actual number. And this is the optimal worst case regret. And the mechanism that implements it is given by this formula. If you offer me, so this is a one project, and I'm just telling you the mechanism, the probability that I will accept a project UV. If V is sufficiently high, if you offer me sufficiently high payoff, then I accept it with probability 1. And if you offer me low payoff, then I accept it with probability that is decreasing in your payoff. Okay, don't know if it's clear what's written here. What's written here is U underbar, which is the parameter, which is the bound on the agent's payoff. Okay, this is the probability that I will accept it. And I intended to prove this, but I don't think I will have time. The proof is rather simple. I want to emphasize one interesting property of this mechanism, that rho UV, the probability that I will accept a project, increases in V, increases in the payoff to the principal. This already existed in Armstrong and Vickers solution, in the delegation solution. It also decreases in the utility of the agent. So if the agent offers a project that gives the agent high utility, I am less likely to accept it. And the reason is that if the agent offers a project that gives the agent high utility, I am worried that he may be hiding actions that are better for me. Okay, so this is the kind of the interesting property of this optimal mechanism, and it's I think it's also an interesting question in the Bayesian environment to find out what are the properties over the prior that will induce this property for the optimal mechanism, but it seems like a difficult question because we don't know what to say about the optimal mechanism in Bayesian environment without assuming deterministic mechanism. Okay.
Are you sure about the expression for the optimal rho star, R star? The minimum, they should not be equal, the two terms in the minimum? Not 1 minus V minus U bar, the second term of the minimum?
I think I'm sure, but yes, you're right. This is the V that makes these two terms equal. And when you substitute this V into this formula, you get this, unless I'm mistaken here, or maybe I'm mistaken, but let's not, I don't think I am because I think I just copied it from the paper, but maybe I made some typo. Okay, but you're right. This is the V that equates these two things, and I just substitute it here. And I just substitute this V here. Okay, so let's, maybe I made a mistake in the last element. Let me, well, I think I can explain to you where this comes from in 1 minute, where this R star comes from, but it will not really be a proof. It will just be a quick explanation. Let's look at the probability that we are going to accept if the agent offers the project that gives the agent utility 1 and the principal utility V. There are two options. Options 1 is that we accept this project with a very low probability, with probability that is smaller than under U. In this case, if this is the only project that is available, we suffer regret of v times 1 minus under u, right? Because we could have gotten v, but we only accept this action with probability under u, and therefore we suffer this regret. On the other hand, if this arrives with probability greater than u, then it may be that the set of available action is this, but there was also an action which is very bad for the agent and very good for the principal. And because we were willing to accept the action 1v with such a high probability, the agent prefer to only propose action 1v. And now we suffer at least 1 minus v, because we could have gotten 1, but we end up getting at most v, because we take this action 1 minus v and maybe also with only with some probability. Okay, so whatever we do, whatever our mechanism does, either we are going to suffer this or we are going to suffer this. So we are going to suffer at least the minimum between these two things, and this is true for every v. Okay, this is where it comes from. Okay, those who followed me followed. I'll say quickly, very quickly, the structure of the optimal mechanism in the multi-action environment. It's what we call the trading mechanism. There is some function P of V. And I'm not going to tell you what is just the P, but we can pin it down exactly, we calculate in the paper. If the agent offers one project, we implement, we take it with probability P of V. We accept with probability P of V. If the agent offers a set, proposes a set, then we randomize in a way that maximizes principal's payoff subject to agent receiving exactly the maximum that the agent could have received if he offered only one project out of this set. And the maximum that he could have received if he offered only one action is the maximum from this set of u times P of V. Okay? This mechanism will make the agent report truthfully, because the more the agent reports, the highest this maximum can be, right? And so the agent doesn't have any interest to hide anything. And subject to his reporting truthfully, he will get this amount, and we will just maximize how much as we can. Okay, and maybe I will just copy to the slide the actual regret that comes out for it, and I will then finish. So this is the regret that comes out of this mechanism. sorry, I should have said that M here is the under U. It's the lower bound on the agent's payoff. Okay. So this is it. We characterize the optimal mechanism in these two environments, and we had some interpretation of what's going on in the one agent environment. The probability of accepting decreases in the agent utility. In the multi-actions environment, we have this trading that is going on. Okay, I'm 2 minutes after time, so thanks a lot, and I am happy to stay. Okay, that's, okay. Let me try to stop sharing my screen. Okay.
Okay. Thank you.
I can answer additional questions if there are.
Yeah, that's the time for questions.
Okay, then.
I was just looking at that formula, Eran, and I was trying to check if what happens when m equals 0, but it went away too fast. And you say it goes from 1/4
okay,
to
so
0,
I can tell
but
you,
I didn't actually see
happened.
1/4. I actually saw infinity because m square was in the bottom, so I made a mistake probably. Can you just help me there a little bit?
Sorry, I mean, I want to be willing to accept the option that I made a mistake here because I just
no, it's
copied
fine.
it
So
from,
you're just, I'm interested in 1/4. So
the paper. So if m equals 0, the worst case regret there is 0, and if m equals 0, then you have to take the limit of the thing. I mean, the formula that I posted, I assume that either it's incorrect or you have, if it's 0/0, then you have to
Yeah.
look at the limit, right?
Sure, sure.
But maybe it's incorrect, so let's not get.
No, but you're saying it's 1/4. You're saying.
Yeah, but it is. I think in the 1/4 we are sure, unless Yeni can say something.
It's very nice.
Yeah.
1/4 result. Yes.
It's 1/4. Yeah.
It's 1/4, and for the single project, it was 1/2. So you gain something with the ability to trade.
And why is it called trade? I don't see the trading there because I just see, yeah, so can you explain?
Like you offer this set of projects, and we don't take the one that is best for me. We don't take the one that is best for you. Among this set of projects, there is one that is best for the agent, and there is one that is best for the principal. We don't take this one. We take some kind of combination between them that guarantee certain payoff to the that guarantee the agent what he could have gotten, like without trading, what he could have gotten if he just reported the one that he likes the most.
May I ask a question now?
Sure.
Thank you. One question. You said it's more on the intuitive level because I do not exactly remember the formulas. You said that you basically reward the agent for giving something which benefits the principal and punish the agent, roughly speaking, for suggesting something that benefits the agent. Makes sense, but if that offer happens to benefit both the agent and the principal, does it still make sense to punish the agent for getting benefit himself too?
So remember that, I mean, I made a mistake that I stopped showing the screen so quickly, and it will take me forever now to upload it again. But remember that my function, the probability that I will accept an action, was increasing in the principal's payoff and decreasing in the agent's payoff.
Yes.
So if you offer something that gives the principal high payoff, you will get it implemented with high probability. But it has to be sufficiently high, right? And sufficiently high depends on.
Question is the following. I mean, I of course I understand why your suggestion is good, why it works, and I trust that you've proven that more than just an intuition. Fine. My question is as follows. Can you maybe improve upon what you've done if you say that if the principal gets enough, then also the agent is not punished for having something, so that you only punish the agent if she gets more than the principal. Because what I mean is that it can be that the agent will not offer something good for the principal, because maybe it's good for the agent to offer something worse for the principal, which is also worse for her.
So the first, in the mechanism that I presented, if the principal gets sufficiently high payoff, the action is implemented with probability 1.
Mm-hmm.
And that was the case in the mechanism I present. You cannot improve the mechanism that I presented because I have a theorem that it is the optimal mechanism. I don't think there is much to do in comparing the payoff of the principal and the agent. These are both von Neumann-Morgenstern utility defines on different things. So,
but now I think I understand why it's optimal. If it's enough for the principal to get a high payoff for the right, you're right. It's kind of okay. Now I recall. Thank you. Thank you.
Okay, good. So if there's no more questions, I'm going to take a second coffee and.
Any more questions, people? Well, if there are no questions, then we thank Eran again.
Okay. Thanks a lot for the invitation and the patience. Okay.
Very good. Well done.
Cheers.